All right, we have more ring theory stuff to talk about. So we're going to start with the definition. So we're going to say that an element is nilpotent if there is some natural number, of course natural numbers don't include 0, such that a raised to the power of n is equal to 0. So turns out that, and I put this as a fact because it's not even like if I were to state it as a proposition, it would take up more than one line, and this is really only a one-line thing. So if we have a nilpotent element A, and any prime ideal P, then we know that A raised to the n is 0 for some natural number n, because that's what it means to be nilpotent. But 0 is in P since every single ideal contains 0. And remember that the condition for being prime means that if A times B is in P, then either A is in B or P is in B. And this we've talked about this. This extends to finite products. So if A1 times A2 all the way through AN, if this product is in a prime ideal P, then AI is in this ideal P for some I between 1 and n. So in particular, if a to the n equals 0, well, if a to the n is in P, then one of the factors of a to the n must be in P. But what are the factors of a to the n? We have a, we have a, we have a again. It's just we have n copies of a, so the only factor is a. And so a must be in P. So therefore, every single prime ideal of a ring contains every single nilpotent element of that ring. All right. And it turns out if you just look at the set of nilpotent elements of R, and we'll call it N, this is called the Nilradical, and I think it might be one word instead of two, like I've written it here. It's either one word or two words, whatever, but it's an ideal. And to prove it's an ideal, certainly it contains 0, because 0 to the power of 1 is 0. If we take a nilpotent element A and an element R and R, okay, so let's prove that it's closed under multiplication by any element in the ring. So let's say a to the n is 0. Then if we take R times A, like we're multiplying A on the left by R, then raising this to the power of n, because this is all taking place in a commutative ring from now on, unless I say otherwise, all of these rings are commutative. Because what we can do then is we can move all the r's next to each other and all the a's next to each other. And so this is just r to the n times a to the n. But a to the n is 0, so this is just r to the n times 0, which is going to be 0 regardless of what r is. So therefore, this confirms that RA is in n. And similarly, if we look at this element, a times r, so now we multiply on the right, raising this to the power of n, this is a to the n, r to the n, which for the same reason is 0, and so AR is an n. So therefore, n is closed under multiplication by any, well, okay, we are assuming this to be a commutative ring, so I guess this part is not necessary, because in a commutative ring, RA is going to equal AR. So it suffices to prove that multiplication on just one side works. Does it? Yeah, if we're in a commutative ring, then it suffices, because that's why we're able to move all the r's here and the a's over. Okay, so this is good. So yeah, so then RA is in there, and then certainly AR will also be in there, and so we're good. This is closed under multiplication by any element in the ring. As for addition, this one's a little trickier. So if you take two elements A and B and N, and suppose that A to the N is equal to B to the M, and both of these things are 0, then when we take A to the B, A plus B, and we raise it to the power of N plus M. And when we do that, we have to remember the Binomial Theorem, where we get the sum from k equals 0 to n plus m plus this binomial coefficient here times a to the n plus m minus k times b to the k. But now what we notice is no matter which k we choose, either the power of a is going to be greater than n or the power of b is going to be greater than m. One of those two is going to be the case. And to make that very clear, what we can do is we can, if we break the sum up, so here the sum is from 0 to n plus m. Let's break it up into going from 0 to m and then from m plus 1 up to n. Here we're assuming without loss of generality that m is less than or equal to n. And we can do that because one of the two is going to be less than or equal to the other. But anyways, so if we say that m is less than or equal to n, well, let's say m is strictly, well, yeah, less than or equal to. And if it is equal to, then we just don't include this term at all. So anyways, what we do is we take this and we go from 0 to m, and here, because the power of a is going to be n plus m minus k, so we can factor out an a to the n here. And basically the reason I'm doing that is that this allows us to avoid using like negative powers. So, right, so we have a to the m, or a to the n, and then we have an additional a to the m minus k. And then we have this b to the k. And so this isn't necessarily going to be 0, but this will be 0. Because we know that a to the n is 0. And similarly here, when we go from m plus 1 to n, here k is going to be greater than m. So what we can do is instead of, so we're raising b to the power of k here. So I guess this has to be k minus m. Right, because when we add these together, it should be b to the k. And because k is greater than m, this is going to be a positive exponent. All right, so, and the reason that we need to make sure that we have positive exponents is that you don't necessarily have negative exponents, because that if you have negative exponents, then the first one is going to be -1. But raising to the power of -1, that's taking the multiplicative inverse. So we can't really, we don't really, in a ring, we don't really know how to deal with negative powers per se. We know how to deal with powers in the natural numbers. That's just you multiply the thing by itself n number of times. That we know how to deal with. We don't really know how to break it up into like a negative power. So we need to do this so that we ensure that all of these powers are positive. And here this all works out fine. And so here, of course, we have this b to the m. This power is clearly going to be positive. This one's going to be positive. And because k is greater than m, this will be positive. And so then this is going to be b to the m. Well, that's 0. So every term here is 0 because there's a factor of 0 here. Every term here is 0 because there's a factor of 0 here. And so the whole sum is 0. So therefore, we have an ideal. Because we've proven that it's closed under addition, it's got 0, and it's closed under multiplication by any element in the ring. Alright, so that's the nilradical and nilpotent elements. Now, for another definition, we say that R is a local ring if it has a unique maximal ideal. And this is, I don't remember if I mentioned this. When we defined maximal ideals, we just said that this is a maximal ideal of the ring if blah, 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 blah. We said nothing about maximality. And it sort of makes sense because when we looked at that proof where we were proving the existence of maximal ideals, we used a partial order on the set of proper ideals of the ring. And we proved that any chain, and we used Zorn's lemma to prove the existence of a maximal element, i.e. an element that is an element of that ring such that no other, or an element of that set of proper ideals, an element of the set such that no other element properly contains it. And that's important because you could imagine, like, if you've got your entire ring R over here, you can have a maximal ideal here, M1, and a maximal ideal, like, over here, M2. Like, maybe they intersect, maybe they don't, I don't care. But it could be entirely possible that, like, so M1 and M2 are both proper ideals of R, but there's no proper ideal of R which contains M1 properly, and there's no proper ideal of R which contains M2 properly. So in this case, both M1 and M2 are maximal ideals, and there's no issue here with these two, both of these ideals being maximal ideals, because one is not contained in the other. They sort of, like, maybe they overlap a little bit, or maybe they're completely disjoint. It doesn't matter. We don't really, in general, it doesn't matter. In general, you can have multiple maximal ideals in a ring. But we say that a ring is local if it has a unique maximal ideal. And so, sort of the dumbest example of this is a field, because the unique maximal ideal is 0, because fields have, we've talked about this, fields have two ideals, 0 and the entire field. And the entire field is not a proper ideal, so the only proper ideal is 0. And so it's, not only is it the only ideal, but it's a maximal ideal. And so it's the unique maximal ideal. For another example, we let K be a field, and we consider this thing. It's sort of like a polynomial ring, but instead of taking finitely many powers, we take infinitely many. So this is basically just like power series that you'll see in real analysis or complex analysis. And we call it the ring of formal power series. With so we don't really have any restrictions on these coefficients. They can be any elements of the field K. And we define multiplication the same way that we define it for multiplication of polynomials. It's just that these sums are now infinite. Well, at least this sum is infinite. This one will always be finite for each number n here. Then it turns out that the ideal generated by x is the unique maximal ideal of this ring R, which is K, and then here this X is in like bold brackets or something like that. I don't know. It's sort of a fancy brackets here. As opposed to if we were considering the polynomial ring, we would just have normal brackets around this X. So you can prove that the ideal generated by X, so this is basically all polynomials where you don't include the term n equals 0. So this is every single, so the powers of x here go from 1 all the way up through infinity, but they don't start at 0. And let's see here, so certainly this is an ideal because you can sort of see by the way multiplication works that if you take a polynomial whose power is, if you look at the smallest power of an element here, then the smallest power is not going to the smallest power of any element here is 1, and the smallest power is not going to decrease if you multiply by any element in this formal power series. Just by looking at the multiplication, you can see that. And certainly adding things together isn't going to decrease the lowest power. And so, let's see here. So that sort of shows you that this, you might have to fill in a few more details there, but this is certainly an ideal. And it's maximal because if you were to add anything into here, then the only place that you could add it in from would be from the, you'd have to have some term that corresponds to k equals 0. So it would just be some constant in the field. But what you can do is, if you consider that polynomial, so you'll have a polynomial and one of the terms will be, the zero term will be a constant in the field. If you look at all the other ones, all the other terms, if you just look at those by themselves, that will form an element of here. And so you can subtract that, and what you'll end up with is just the constant from the field by itself. And if we, without loss of generality, suppose that this is a non-zero element, because certainly it's not, if it were zero, then that wouldn't be interesting, because zero is already in here. So if we take a non-zero constant in here, then since this is a field, it has a multiplicative inverse, and by closure under multiplication, this ideal, the new ideal will contain 1, and so it will contain the entire ring. Now, proving that's the unique maximal ideal, I think that might take a little bit more work, but it shouldn't be too bad. But I don't want to dwell too much on these examples. And this is more of like an interesting thing to think about. But anyways, so now we have a lemma, and so this makes sense. Let me just make sure. How am I doing on time? Not great. So let's see here. So let's do this lemma. R is local if and only if the set of non-units, which we will call M, is an ideal. And so it's an if and only if, so we got to prove two directions. Let's start with the forward direction. Suppose R is local, that means it has a maximal ideal. Let's call it A for now. So if the set of non-units is equal to A, then it's an ideal because A is an ideal. Okay, so let's try to aim for that. So since A is not equal to R, A must be contained in M, because since A is not equal to R, it cannot contain a unit, because if it contained a unit, then it would contain 1, and then it would contain all of R. And so all of its elements are non-units, and so therefore it's contained in the set of all non-units. Okay, so we have A is contained in M. For equality, we want M contained in A. So let's take some element M in capital M. Then the ideal generated by it is a proper ideal in R because, well, it's not the whole ring because it's not a unit. So therefore, the ideal generated by this element M is contained in A. Because A is the maximal ideal. And so therefore, but this holds for every single M in capital M. And so in particular, we know that every element of capital M is in A. And so M is contained in A, and so we have equality. So in particular, M is an ideal. So that's the forward direction. For the backwards direction, suppose the set M of non-units is an ideal. So now suppose we take any proper ideal. Suppose we take any ideal A which properly contains M. Since M is a set of non-units, the fact that A properly contains M implies that A must have a unit. And so in that case, A is equal to R. So what this tells us is that M is a maximal ideal, because any ideal which the only ideal which properly contains it is the entire ring. So it is a maximal ideal. We want to prove that it is the maximal ideal. So let's take any proper ideal A and R. In order to say that M is the maximal ideal, we need to prove that A is contained in M. So proper ideal A contained in R, then since it's proper, it cannot contain any units, because if it did, then it would be the whole ring. So it does not contain any units, and so that means it must be contained in the set of all non-units. So in particular, meaning it's contained in M. So not only is M a maximal ideal, it is the unique maximal ideal because it contains every proper ideal. And so if you had another maximal ideal, then, Well, if you have any other idea, any other maximal ideal would be a proper ideal, and thus would be contained in this maximal ideal. And so in that case, it's either equal to this or it's not maximal. Okay, but anyways, this proves that M is the unique maximal ideal of R, and any ring which has a unique maximal ideal is local, and so hence R is local. And this completes the lemma, and that completes our discussion of nilpotent elements, the nilradical, and local rings.